Hello, my name is Kamron Abdulkhaev. First of all, I want to thank the organizers for the opportunity to give this talk. Today, I'm going to present my joint work with Professor Dmitry Shirokov on explicit formulas for characteristic polynomial coefficients in geometric algebras. Our presentation comprises 5 main parts. First, we'll make introduction and show some background of the problem. Then, we'll provide some necessary notation and definitions. After that, we'll display our main result of the paper, namely explicit formulas for the characteristic polynomial coefficients in geometric algebras for the cases n equals 4 and 5. Then, we'll provide some insight into our technique of the analytical proof of the result. And finally, we'll make a conclusion of our work. Let us proceed to introduction and background of the problem. Characteristic polynomials in geometric algebras were previously discussed in Professor Jacques Helmstedt's paper Characteristic Polynomials in Clifford Algebras and in More General Algebras. Characteristic polynomials were also considered in the paper on computing the determinant, other characteristic polynomial coefficients, and inverse in Clifford algebras of arbitrary dimension by Professor Dmitry Shirokov. Now, let us provide some necessary notation and definitions. First, let us consider the Clifford or geometric algebra GPQ, where sum of P and Q is equal to n, with n generators from E1 to En, and identity element E. The generators satisfy this condition, which means that the generators anti-commute with each other and the squares of first P generators are equal to +1 and the squares of remaining Q generators are equal to -1. We denote ordered multiplication of k different generators with multi-indices and call them the basis elements with multi-indices of length k. We call the subspace of the linear combination of these basis elements the subspace of grade K and denote it by GPQK. Let us introduce the operation of projection onto the subspace of grade K. The projection of any geometric algebra element U on the subspace of grade K will denote by U in angled brackets with subscript K, or sometimes will omit angled brackets and leave only subscript K in order to simplify notation. This operation is linear. Important to say that we identify elements of grade 0 with scalars. We will frequently use the special case of this operation, the projection of element U onto the subspace of grade 0, which we'll call the scalar part of U. This special case has the following property number 3. Let us introduce the operation of conjugation in geometric algebra. We'll call any operation which changes given element signs of subspaces grades an operation of conjugation. We have 3 classical operations of conjugation: the grade involution, the reversion, and the Clifford conjugation. These operations have the following properties number 8. Alongside these classical operations of conjugation, we also frequently use one additional operation of conjugation, triangle operation, which we will denote by triangle. In contrast to classical operations of conjugation, in general case, this operation does not have similar properties. However, we discover that the triangle operation has the following property number 10. This property is weaker in relation to presented earlier properties of classical operations. We'll show them in more general case later. Let us define the characteristic polynomial in geometric algebra. Let us have an arbitrary geometric algebra element U. We call the characteristic polynomial of U following expression, where characteristic polynomial coefficients, capital letter C's, are elements of grade 0, which we identify with scalars, and beta is a matrix representation. The main idea of this construction is to connect the concept of characteristic polynomial from matrix theory with geometric algebra. We also need the following recursive formulas of the characteristic polynomial coefficients. By this theorem, the coefficients could be calculated in the following way. We set for the first auxiliary term element u. Then, using the scalar part operation on the term, we calculate the first characteristic polynomial coefficient. After that, using this formula, we compute the second auxiliary term. Then, once again, by taking the scalar part of this term, we get the second coefficient. So, continuing to recursively calculate, we get all the coefficients. Also, these formulas let us compute the determinant, the adjugate, and the inverse of an arbitrary element u. The problem of finding inverse were discussed in multiple articles by several experts. In particular, by Professor Arthur Arcus and Professor Adolf Dages in their paper The Inverse of a Multivector Beyond the Threshold P plus Q equals 5, and by Professor Eckhard Hitzer and Professor Stefan Zangweiner in their paper Multivector and Multivector Matrix Inverses in Real Clifford Algebras. In the cases n equals 1, 2, 3, and 4, we have the following explicit formulas for the characteristic polynomial coefficients. They were obtained in the previous papers, but for the first time we present full analytical proof of the explicit formulas for the characteristic polynomial coefficients in the case n equals 4. In the cases n equals 5, we found explicit formulas for all characteristic polynomial coefficients in geometric algebras. We verified them using computer calculations. Note that these formulas are basis-free and involve only the operations of geometric product, summation, and operations of conjugation. Note that if we ignore the triangle operation, the presented explicit formulas for the characteristic polynomial coefficients look like elementary symmetrical polynomials in the variables u, great involution, reversion, etc. Let us give some insight into our technique of the analytical proof of the result. For our proof, we will need these two lemmas. The first lemma is for simplification of the expressions. As you might notice, properties from first lemma are general case of previously discussed weaker property of triangle operation. Interesting to note that properties 12, 13, and 14 are a simple consequence of the property 11. The second lemma is for the final step of the proof. It shows the relation between the operations of conjunction, left-hand side of the equalities, and the great projection operations, right-hand side of the equalities. Note that the same left-hand side of the equalities could be used to realize the scalar part operation in the cases of smaller dimensions n. As an example of our technique, we'll show the proof of the explicit formula of the second characteristic polynomial coefficient in the case n equals 4. Our proof is in two steps. Step 1. First, using recursive formulas from the theorem 1, we calculate C2. Then, using lemma 1, we simplify obtained expressions. After simplification, we get expression number 33, which differs from actual formula only by scalar part operation. Now we know that the scalar part of this expression is equal to second coefficient. Let us prove that taking scalar part is unnecessary. In other words, we have to show that this expression inside the scalar part operation is the element of grade 0. One could notice that the sum of first and last term does not change under this operation of conjunction. This means that this sum belongs to the subspace of grade 0. As for the remaining 4 terms, they can be regrouped as follows. Then, using lemma 2 and expanding brackets, we see that the expression belongs to the subspace of grade 0 too. Hence, the sum of all terms is the expression of grade 0, and scalar part operation could be omitted. This concludes our proof of the explicit formula of the second coefficient of the characteristic polynomial in the case n equals 4. Other coefficients of the characteristic polynomial are proved in similar 2 steps. In conclusion, for the first time we present full analytical proof of explicit formulas for all characteristic polynomial coefficients in the case n equals 4. Also, for the first time we found explicit formulas for all characteristic polynomial coefficients in the case n equals 5. The characteristic polynomial is one of the basic concepts of linear algebra. It has both theoretical and practical importance. We hope that our result will find its application in the space-time algebra signature 1-3 in physics, and in the conformal geometric algebra signature 4-1 in computer science and engineering. We also plan to show explicit formulas of all characteristic polynomial coefficients in the case n equals 6 in extended version of our paper. Thank you for your attention. We will be glad to answer any questions.